In today's video, I'll be going over some of the history of chemistry, as well as the early attempts to explain the structure of the atom. First, we have to talk about the ancient Greeks. They were the first to try to explain the phenomenon of chemical changes. They proposed that all matter on Earth was made of four basic elements: fire, earth, water, and air. Of course, this couldn't be farther from the truth, as we know today. The philosopher Democritus believed that matter was composed of small, indivisible particles. Therefore, his theory suggested that matter could not be divided further beyond these particles. Future philosophers used the name atomos for these particles, which later became the word atom. However, the ancient Greeks lacked the knowledge and equipment necessary to run experiments, and therefore could not prove any of their theories. Next, we have to talk about alchemy, which nowadays is regarded as a form of pseudoscience. Most alchemists were trying to find a way to turn cheaper metals into gold, which wasn't possible. However, alchemy did prompt some real advancements, such as the work of George Bower, who figured out how to systematically extract different metals from ores. One important scientist from the end of the alchemy period was Robert Boyle. He was the first to perform quantitative experiments on the behavior of gases, and he developed a law that explains the relationship between pressure and volume of a gas, which is an important concept in thermodynamics. Additionally, Boyle's view on elements was that any substance that could not be broken down into simpler ones was an element. By the 17th century, the known elements included metals such as gold, silver, mercury, iron, lead, tin, and copper, as well as sulfur and carbon. Next, let's talk about what early scientists thought about combustion. Today we know that combustion occurs as a result of the reaction of oxygen, fuel, and a heat source. However, the explanation created by early scientists is far different and seems somewhat silly today. The chemist George Stahl believed that a substance called phlogiston flowed out of a burning substance. He asserted that the reason why a flame in a closed container will eventually die is because too much phlogiston builds up in the air inside. However, we now know that it's because the flame runs out of oxygen. English scientist Joseph Priestley was the first to isolate oxygen in its pure form. However, he still believed in the phlogiston theory and reasoned that oxygen must be low in phlogiston because it was found to support vigorous combustion. It was the French chemist Antoine Lavoisier who finally discovered the true nature of combustion. He ran experiments in which he carefully weighed the reactants and products of various reactions, which led him to prove that mass is neither created nor destroyed. His results showed that combustion involved oxygen, the same gas that Priestley discovered earlier. In 1789, he published the first modern chemistry textbook. In the 1800s, many scientists followed the lead of Lavoisier. Joseph Proust discovered that, in the formation of a compound, the atoms of different elements come together in whole number ratios. For example, in CO2, which contains one carbon atom and two oxygen atoms for every molecule. The discovery of the law of definite proportions by Proust prompted John Dalton to think about atoms as the particles that might compose the elements. He reasoned that any given compound should always contain the same combination of these atoms. He also noted that carbon and oxygen naturally form two different compounds. Let's take a look at the following data. We can see that in compound 1, there are 1.33 grams of oxygen per 1 gram of carbon in whatever this compound is. And in compound 2, there are 2.66 grams of oxygen per the same 1 gram of carbon. So there's twice as much oxygen in compound 2. By experimenting with other compounds, Dalton found that this difference will always be a whole number ratio, as in it will only ever be double, triple, sometimes quadruple the measurement, and never something like 1.5 times more. This showed that elements are composed of units that cannot be split and combine in whole number ratios, such as CO, or 1 carbon for every oxygen, and CO2, where 1 carbon combines with 2 oxygens. Let's take a look at this example. Here we have 3 compounds, each composed of some combination of nitrogen and oxygen atoms. On the right-hand side, we have the amount of nitrogen per 1 gram of oxygen that was measured out of samples of these compounds. Let's divide the amount we found in compound 1 by the amount in compound 2. When we do this, we get an exact 2-to-1 ratio. When we do this with compounds 2 and 3, we also get a 2-to-1 ratio. And when we divide compound 1 by compound 3, we get a 4-to-1 ratio. Therefore, relative to the amount of oxygen, compound 1 contains twice as much nitrogen as compound 2, which contains twice as much as compound 3. In all, Dalton's findings led him to publish his atomic theory, which said that each element is made up of atoms that are identical for a given element, that they combine in a constant whole number ratio to form a given compound, and that a chemical reaction only involves the reorganization of atoms and what they're binded to, and that the atoms themselves are not modified.